begin our discussion on semiconductor and solid-state physics, and we're going to start by talking about semiconductor materials and crystalline structures. Now, I'm not going to define semiconductor yet, but we'll start by naming some examples of some semiconductors. So I've put up here a list of a bunch of semiconductor materials. And a good way to recognize whether or not something is a semiconductor material is using a periodic table. So, for example, carbon is an example of silicon, carbon, germanium, these are all examples of semiconductor materials in the sense that you can bond them together. So, for example, silicon will form tetrahedral structures like this, similar with carbon, similar with germanium. Other example, and then also they can form tetrahedral structures with each other. So you can see like silicon carbon bonds form, silicon germanium bonds form, and so these are some examples of some semiconductors. But then also, these are considered the group 4 semiconductor materials because they occur with group 4 elements. But you can also find binary semiconductor materials like boron nitride, or aluminum phosphate, or gallium phosphate, or aluminum arsenide, or gallium arsenide. And each of these semiconductor materials has their own variety of properties and their own unique use case. Similarly, you can go down the line with the periodic table and look at other semiconductor materials like zinc sulfide, zinc oxide, zinc selenide. And these are, again, more examples of semiconductor materials, each with their own unique property. And these kinds of semiconductor materials, as you see over here, are called binary semiconductor compounds. But you can also have tertiary semiconductor compounds, which are made up of 3 different semiconductors. For example, gallium phosphate arsenide, which is a semiconductor material is an alloy, because you have a certain amount of gallium, because half the crystal will be gallium, but then a portion of it will be phosphorus and a portion of it will be arsenide to match up with the compounds. And so this is an example of a tertiary semiconductor material. And combining these together, each of these semiconductor materials have their own unique properties, of which, for example, gallium arsenide is particularly used for LEDs, and so forth with all of these different materials. Now, the key to understanding the structure of these semiconductor materials, as we started looking here, is through lattices and crystals. So all of these materials, when they form together and bond together, they form lattice shapes. And these lattice shapes come in 4 different varieties, at least for what we're concerned with. We have the first kind that we'll talk about is simple cubic lattices, which is where you just have an atom on every single corner. And so this is how the atoms bond together. Then you have, and we'll label this as simple cubic. Then we also have body-centric lattice, which is actually very similar to the simple cubic lattice, except now there is a atom in the middle. And so we call this body-centric lattice. Body-centric. And then third, we have face-centric cubic, or FCC, which again, is kind of like simple cubic, except now every single face has a atom in the middle, like this. And up here and down here. So one thing we can do with these lattices, and then the last one is called diamond-centric lattice, which is a very common lattice shape for a lot of semiconductor materials. Silicon, in fact, silicon, which is the most important semiconductor material, follows this structure. It's very similar to a face-centric lattice, except, well, it's almost like a combination of two face-centric lattices. So it's one face-centric lattice, and then also the atoms of another face-centric lattice offset by 1/4 in all directions. So looking at the diagram, you can think of it as there's an atom here. Well, then there's another atom also here, because that's an atom offset by 1/4. Similarly, here there would be another atom right here, because that's the same face-centric atom, but offset by 1/4. Here there would be another one that occurs up here, and likewise for all these atoms, right? There would be, in whichever unit cell is above this unit cell, there would be an atom right here, above and to the left. There would be an atom right there that's offset by this corner atom. And so this is called diamond lattice. Many crystal structures for semiconductor materials are formed in this. For example, silicon, like I said. Also carbon forms in these shapes, which is why it's called diamond, actually, because diamond crystals form in this lattice form. And so these are the four main lattice structures that we need to know. Now, we can analyze certain properties for these lattice structures. For example, how many atoms are in each? So in a simple cubic, for example, we can count how many atoms there are. Since each of these corner atoms since the space of the unit cell is only occupied by 1/4 of the atom, we can just add up 1/4 times the number of atoms in space, which is 8, and we can say that this lattice structure is occupied by 2 atoms. You can do a similar math with the body-centric, and and we can say that the body-centric atom would have, not 1/4, 1/8. My mistake. Here, each atom would occupy 1/8 of, the space would be occupied by 1/8 of each atom, and since there are 8 of them, it'd be 1 atom. For body-centric, it would be 2 atoms because you just have that atom in the middle. For face-centric, you would have you would have 1 atom for each of the corner ones, but then also you would have 6 face-centric atoms, each of which half of the atom occupies the space. So 4 atoms occupy face-centric. And then for diamond, since it's two face-centric atoms, it would have, since it's 2 face-centric atoms overlaid on top of each other, it would have 8 atoms, right? And so you can see here, one of the properties we can look at is how many atoms there are. And we can actually use this to then, alongside what's called the lattice constant. The lattice constant just describes what the length of the unit cell is, right? And it's usually measured in Armstrongs, and sorry, not Armstrongs, angstroms, which is 10 to the minus 8th centimeters. And so using the lattice constant alongside the number of atoms, you can actually calculate densities of different materials, right? It would just be whatever the number of atoms are divided by the number of angstroms, the lattice constant, which is in angstroms, and then you just convert to density using Avogadro's number and molar mass, and convert from angstroms to like something like cubic centimeters or cubic meters, and you could find the density of these different materials based on their lattice structures. And so you can imagine that something like diamonds would be way more dense than a simple cubic structure. Now, one more property we can look at for lattice structures that's important is like different planes of a crystal. So for example, if I want to describe, for example, this plane of the crystal, and this will be important, understanding the different planes of crystals will be important later on when we look at like different energy levels going on inside a crystal. But if, for example, I want to describe this plane of the crystal, the way you do it is by looking at its orthogonal vector. So for example, this plane is called the 1, 0, 1 plane. And the reason for that is because if we take the vector that goes 1, 0, 1, we have a vector that points in this direction. And the plane that's orthogonal to that is this one. So we call it the 1, 0, 1 plane. And we label the vector like this, and the plane with open parentheses like that. Similarly, you could, a similar exercise, we could say that the plane for the 1, 1, 1 looks like that. For the 1, 1, 1 plane looks like that because the vector that's orthogonal to it points in that direction. So this is another useful property for crystal structures that one should understand. And it's also useful because this orientation tells you actually like exists like macroscopically as well. And so you can see it in the way that you cut silicon wafers or cut semiconductor materials. And I'll show that in this one video I had. So you can see here in this video, this is a silicon wafer, and you can see how the 1, 0, 0 orientation is oriented on the silicon wafer by the way that it breaks, right? So because it breaks in that direction, that's the 1, 0, 0 orientation, and you'll see that no matter how many times you break it, it always breaks in that direction because that's like the weakest orientation, and that's the direction the crystal takes. And silicon being so pure as it is, you can see how it's like a perfect straight line, and there's no defects in like when it's cleaved or when it's cut like that. So those are the main properties to know about lattice structures. The next thing I wanted to show or talk about was how these crystals are manufactured or created, and specifically silicon, since that's the one we'll focus on, and that's the one we'll focus on. So when silicon is manufactured and we get like these silicon wafers that you see in this image, it's incredibly pure, and the way that they do that is through a chemistry process, a chemical manufacturing process where they just drive carbon through it. They take sand, which is silicon dioxide, they run a bunch of carbon through it to purify it. They run a bunch of HCl acid through it as well to remove all the impurities, and they're just left with this like vat of molten silicon, which is clean due to all the processing with the carbon and the HCl, and also I should mention hydrogen as well. But you're left with this vat of molten silicon, and what they do is they take something called a seed crystal, right? which is already crystalline structure, and they dip it into the molten silicon and then let the silicon cool, so that when the atoms then start to bond to this seed crystal, they form the shape of the crystal that we want, until we get an ingot of silicon that looks like this. And then it's very easily sliced or sawed into silicon wafers because of the very pure properties of silicon, and because its lattice structure is so perfect, we can easily saw it into perfect silicon wafers. And so that's how silicon is manufactured, and these silicon wafers are created. It also shows the unique control that we have over silicon to be able to make it so pure. There's really no other element that we can do this kind of clean purifying with and get such perfect lattice structures as we can with silicon, which is one of the reasons that it's such a powerful semiconductor. That's all for the main properties of semiconductor materials and their crystal structures. Next video, we'll look at bond diagrams and using them as a model to describe the properties of semiconductors. Thank you for watching, and please like and subscribe.